Hi, my name is Malt. Let me walk you through quickly through the dimension reduction technique available in Bundleverse. Why does it matter? It matters because it's a way to analyze your data and visualize your data, and there is a mission so we can collect a lot of data, and if we take a snapshot of this data, the data collected during one day, for example, it could have 20 variables, for example, could be collected in one day, and those 20 variables, you may think of it as just one dot point in this 20-dimensional space. And if you run this mission for many days, you may have hundreds of those data points in this 20-dimensional space. And the question which follows is, you might be curious about the distribution of those points in this 20-dimensional space. Are there any clusters, for example, or are there any tendencies? What happens with time with this data? Are they just drifting in some directions? Or maybe they are forming some interesting shapes. And that's where dimension reduction steps in, because you cannot visualize this data in 20-dimensional space. You need to project this data into lower dimensions, 3 to 1 dimension, in order to analyze it and visualize it and make some inferences about their distribution. Now let's start with a simple example. We have two clusters here. They are defined in 3 dimensions. Each cluster belongs to a plane. All those points belong to a plane which crosses the 3-dimensional space. Orange points belong to one plane and blue points belong to another plane. Now assume there are 2-dimensional beings which cannot see in 3 dimensions. In order to analyze those points, they need to project them to 2 dimensions. And to keep it simple, let's assume they are projecting it onto the horizontal plane. And I see on the horizontal plane 2 shapes, roughly like ellipsoid shapes. Ellipse shapes is shaped like an ellipsis with some distances in between. They can figure out that we are likely to have 2 clusters in 3 dimensions as well. Now assume that they decided to project those points not to the horizontal plane but on the side wall here. Then, as you see here from this image, it's likely that some of those points will collide with each other when they are projected on the side wall. And they will have, instead of 2 ellipses here, they will have a more complicated shape. And making inferences from this data would be much more difficult. The point is that the way you project data from high dimensions to low dimensions does matter. And different techniques impose different constraints on these procedures in order to get as much information as possible from those projections. Some require, for example, for those projections to explain as much as possible the variance in the data. If the data is aligned along one specific dimension, for example, they would allocate this projected plane, at least one axis of this plane, to be aligned with this direction. If the method is concerned primarily with the distances between points, so that 2 points which stay far away from each other, when we project them to lower dimension, we would like them to stay away from each other as well. Now, it's not always possible to achieve this requirement to preserve the distances between those points, but the method tries to preserve as much as possible this the relationship in terms of distances between those points. And there are some other techniques. Now, let's see what those 2-dimensional guys can learn about those clusters if they log into Bundleverse and analyze this data with tools available in Bundleverse. On the view page, at the bottom you see this projection button. Click on it and you are going to be redirected to this page, dimensionality reduction page. There are several databases available here. Click on test dataset which is a data set we just looked at. That's two clusters in 3 dimensions, in 3-dimensional space. Now you can select different reduction techniques here and different dimensions. You can reduce it into 2 dimensions or 3 dimensions. And the left plot shows here the projection onto the 2-dimensional space by principal component analysis. That's a method which cares about explaining variance in the data. And as you see here, our 2-dimensional guys will be able to discriminate between those two sets of points quite well. Now, the colors on those plots, they indicate timing of the records. The dark colors are points, are logs conducted at the beginning of the mission. The yellow colors are indicating times closer to the end of the mission, and the bluish and the greenish colors are somewhere in between. And as you see here, and the star, by the way, here is the goals that we set to achieve in this mission. Now it's artificial data, of course. It has very little meaning, but if it were real, what we would be able to see here is that we started with a cluster which is allocated around our goals, and eventually through the mission we drifted away into another cluster, way away from our goal point, our target point. Now on the right hand side here you can see 2-dimensional projections for different methods. PCA, that's the method explaining variance in data. MDS, multidimensional scaling, the method which is aiming at preserving the distances between points, and stochastic neighbor embedding, that's probabilistic method. And as you see, all these methods are able to delineate between those two clusters quite well. Now, at the bottom of this page, at the left, you can see general information of the data, about the data, the number of samples, number of dimensions, and the names of the dimensions and the period. Those data sets, time period, these data sets represent. And for principal component analysis, it tells us how much variability this data explains. 95%, it's quite a lot. If we switch into 3 dimensions here, we will have 100% of data explained by this projection, which is to be expected, because all this data set belong to 3-dimensional space. You don't need to go into extra 4th dimension in order to explain this shape and those distances. Now all calculations here are carried out by your browser, by my browser in this case, and the best way to analyze these data sets, of course, it's on a wide screen rather than on a phone. Now let's switch to multidimensional scaling. The only one item I would like to mention here is that there is so-called stress parameter calculated by this method, which tells you how much distortion have been applied to the distances between those points when they were projected to lower dimensions. Okay, in 3 dimensions the distortion level, the stress, is 0, but when we look into 2 dimensions, since we are projecting from the 3 dimensions to 2 dimensions, there are still some distortions happening, and we have some distortion, some stress level here. The stress level is fairly small, so the data is quite reliable. And with regard to stochastic neighboring technique, the key parameter here is this perplexity parameter. The larger this parameter, the larger clusters this method is trying to form. When you move this perplexity parameter to the minimum, then the method tries to do hair splitting and tries to allocate every 3 dot points in a separate cluster, etc. You see, it's hard to tell what's going on here. It's quite messy. You cannot see those two clusters with this level of details. But if we move this perplexity parameter up, then we can see those two clusters here. And this image is for the parameter which is close to 30, I think. Anyway, now let's have a look on real data sets. That's the data sets have been collected over almost 3 months, 88 samples, 24 features it has. So we are projecting data from 24-dimensional space. And let's start with PCA again in 2 dimensions. As you see here, the goals are here. And there is some tendency, we can see the data. We are drifting, but we are drifting anywhere but not towards our goals, meaning that either our goals are wrong or something is wrong with the way we conduct our mission. And I cannot see any kind of clustering here. Just only one cluster, basically. Let's see how much variance. 30% of variance explained by projecting to 2-dimensional space, not much. Let's switch to 3 dimensions. We're projecting from 24-dimensional space to 3-dimensional space. Again, we can see some tendency in the data sets. Again, missing our target. A little bit more variance explained, but not much, meaning that the data sets we are collecting are too hairy. We cannot confine them within a 3-dimensional space. There are a lot of variability across many different dimensions. Now let's move on to multidimensional scaling. Again, similar behavior. We are moving, we are drifting somewhere, but surely not towards our goals. With regard to this method, again, the stress level, how much distortion we have caused to the distances when we are projecting, quite a lot, much more than 0.1, as you see here. And with regard to stochastic neighboring, well, it's hard to tell what's going on in here. We got just one big lump here and some isolated clusters here. So the bottom line, after analyzing this data with this dimension reduction technique, what I can say is that I cannot see any definite clusters in these data sets. I can see a tendency, a drift of this data. Unfortunately, this drift is in the direction which is anywhere but not towards our goals. So either our goals must be reconsidered and adjusted, or the way we conduct our mission, I conduct my mission, should be analyzed and refined. And that's it, almost. There are other data sets as well. One is about accumulator and the data we collect with timers. And the twist here, the interesting feature of this data set is that we can, rather than looking on how this data evolved through time for our mission, we can compare this data set, our data set we collected. I think it's the last snapshot it's collecting. It's comparing with the data collected by other members of bundle. So you can compare your point with the points in this high dimensional space created by other participants, other members of bundles. You can compare your results with the results by other people. And that's it. I think I'll talk more about those two data sets in another talk. That's all I wanted to share with you in this talk. Thank you for your time. Take care. Bye.